Right, so up till now, everything we've been dealing with has been a direct current circuit. So basically, when we've talked about connecting things up to a battery, well, a battery is a direct current voltage source. So with a direct current circuit, what you've got is you've got a constant voltage source, aka a battery, that drives a current that flows in one direction. So we've been able up till now to talk about the direction of the current, and it just means one thing once you get the circuit set up and running. So here, if I've got a direct current circuit, notice I got a couple batteries stacked together, but basically what this means is I know that the current is going to flow in this direction around the circuit, and it's always going to flow in that direction around the circuit. With an alternating current circuit, what actually happens is that I have an alternating voltage source. It's going to alternate with a sine wave pattern, a sinusoidal pattern. It's going to therefore drive a current that also oscillates with a sine wave pattern. So basically what's going to happen with an alternating current is that you're going to have, it's going to go in this direction and then come back and go in that direction, and it's just going to oscillate back and forth. So this is an alternating current, and these are AC circuits that we're going to be dealing with. So graphically, right, again, thinking about our DC circuit first, well, if you were to plot, say, the voltage as a function of time for our DC circuit, we talked about you close the switch and there's some transient period where your circuit may be getting set up. Then there may be some period at which it's operating at a steady state. And then again, when you open the switch to break the circuit, there may be some, again, transient period that your circuit goes through as the voltage drops back down to zero. With our AC circuits, however, what you're going to see is you're basically going to see a voltage source that does like this. So it's going to generate voltage in a sinusoidal way. And so we're going to end up with voltages that basically plot out like sine curves, and then we're going to end up with, that's going to end up driving currents that will also plot out like sine curves, like this. So notice here I happen to have a current. There's some peak value for the current. Again, as with anything that has a sine curve, there are a couple things I need to pay attention to. One is what's the period of that curve, and that's just how long does it take to go through one cycle. What's the amplitude of that curve? That, again, in this case, since we're plotting the current here, corresponds to the peak current. And then one of the things that we'll talk about is we'll talk about the frequency. So the frequency f, how it relates to the angular frequency, and then how that relates to the period. So here's the relationship that we can use to relate frequency, angular frequency, and period. And then the other thing that will be very useful is, well, we can characterize what's going on by the peak curve value. But obviously, since this is changing, one of the things that we often do with things are changing is we talk about the average. But if you were to average out this curve over one period, you'd actually get zero, because there's a point up here that has a positive value for the current, point down here that has a negative value for the current when it's flowing back in the other direction. If you were to add up what's going on up here to what's going on down there, you'd always get zero. That's obviously not a useful value here. So instead, what we do to talk about an average current is we give what's known as an RMS. So the RMS is basically doing you sort of read this backwards. So the first thing you're going to do is you're going to square all these values, then you're going to average, right? Root, mean, square. So you're going to square them first, take the arithmetic mean, the average, and take the square root to get yourself back to something that's current. And when you do that, what you find is that the RMS value happens to be related to the peak value of the current in a very special way if your current is described by a sine curve. So here, where we do have a sine curve, then the RMS value is just going to be 1 over the square root of 2 times the peak value. Now, what we'll see is that we'll have a voltage source, we'll have a current. Those two things will often have a phase difference between them. So, and sort of whether we choose to put it in the voltage source or whether we choose to put it in the current is a little bit irrelevant. But there will be, the important thing is that there will be a phase difference between, or can often be a phase difference between, the current and the voltage within an AC circuit. Again, with the voltage, same idea. We'll talk about the RMS voltage. Again, it's related to the peak voltage by just being 1 over the square root of 2 times the peak voltage. And so these are sort of the fundamental kind of concepts that are underlying what's going to go on with AC circuits. So we're talking about sinusoidal voltage source. It's going to drive a sinusoidal current. We can relate the frequencies and the period together the same way we can anytime with a sine curve. And then there will be a phase shift. Often will be a phase shift present when we talk about the phase of the current relative to the phase of the voltage.